So welcome everybody. So we are very pleased to have Shamik Banerjee from IOP Bhubaneswar, who's going to tell us about celestial amplitudes for massless particles in 4D. Now, Shamik, of course, does not require any introduction in our community. So just a few things about these lectures. So these are going to be a relaxed set of lectures. In fact, we don't even know when they're going to finish. So we leave it completely up to Shamik to decide when, what the natural end point to the seminar series is. So each lecture is going to be an hour, so that we don't go. It will be just 1 hour for each seminar, and it will be Tuesdays and Thursdays, 3 p.m. to 4 p.m. So those dates are fixed. It will be the same Zoom link. So we are not going to change the Zoom link. So you just click. So you, in case you don't get an email, just click on the old Zoom link. It will work. And please unmute yourself and ask questions. I think before we start, it's a good idea for all of us to mute ourselves. But when you do ask a question, remember to mute yourself back. So with that, Shamik, please.
Yeah, thanks. Thanks for giving me this opportunity to talk here. Okay, so the thing is that, I will be talking about some things which actually I'm working on for the last 2-3 years. So this is about some kind of, well, what should I say, some potential formulation for flat space holography. Now, I mean, that's of course a very ambitious thing, but let's see. I mean, well, we can do something useful or something new here. So let's see. So I'll actually, so in this first lecture, I'll just be talking about the basic things. Okay, so I'll start with the massless particles. So in 4D, so I'll be, so the first is the first thing is that I will be talking about massless particles. Okay. Okay, and then the second constant is that 4-dimensional space-time. So there is an interesting story in higher dimension, but the thing is that, well, I'll be talking about the 4-dimensional space-time only. Okay, and the point is that, well, I'll not be talking. Well, so as far as the scattering amplitudes go, I'll be talking only about the tree-level scattering amplitudes of massless particles. Okay. In the loop, of course, there are other things which happen, but we will not be talking about them. Not just in this lecture, but also in the rest of the lectures, actually. Okay.
So I had one quick.
Yeah, just go ahead. Yeah.
So it's more like an administrative question. Are we recording these videos?
Yes, we are recording this video.
Okay.
Yes, they will be put up on this Bootstrap website that we have.
Okay, thanks.
Yeah, so let me start with this thing actually. So the thing is that, so what is a celestial amplitude? So okay, so for that we first talk about the celestial spheres. Okay, so celestial sphere is, so in 4D, so this is just the, so let me draw the Penrose diagram for the Minkowski space. Okay, and the thing is that the celestial sphere is a space-like cross-section of the future or the past null infinity. Okay, so this is the, sorry. Oh. So this is chi plus, this is chi minus. Okay, and these are space-like cross sections. So this is topologically an S2. So both of them are S2, and this S2 is essentially S2 in the picture is essentially what we'll call the celestial sphere. Okay. And it is essentially all, and another description of the another description of this is essentially this is a space of null directions. Okay. So now let me write down some more equations. So we start with the Minkowski space with the metric.
Hi.
Yes.
Hello?
Yeah.
Sorry. So is this always H2 like in higher dimension? This is going to be modified, right?
Yeah. So S2 or it will be some SD. I mean SD minus 2. D is the space-time dimension.
Okay. Okay. And another thing that you mentioned that it's in higher dimension, it's going to be, I mean, dimension greater than 4, it's going to be much more interesting. But
No.
what about lower dimension?
No. Wait. So that's not what I actually said. The thing is that what I said is that in higher dimension, in dimension D greater than 4, you have an interesting story, but we'll see that it is, well, at least to the extent I know, the most interesting story is in 4D. So that we'll see actually at the so in the like in the saying down the line after 2-3 lectures, we'll see that the 4th dimension is somewhat special, and that makes it interesting actually. Yeah.
And is the formulation is possible in like less than 4 dimension, like 3D?
Yeah, formally you can of course do it. Yeah, in fact the point is that I did not give any reference, so I will do it now. So there actually you will see that it is also done in three dimension. Okay, but the thing is that the scattering amplitudes in 3D, they are somewhat here. So I'll not be talking about 3D. So I'll only be talking about the 4th dimension. Okay.
Okay. Thank you.
Yeah. Okay, so this is the metric of the Minkowski space. So these are the space directions, and the thing is that we can you can go. So it is useful to go to the spherical polar coordinate. Okay, and also you introduce the retarded time u, which is t minus r. You can also do the advanced time, but the point is that we'll be looking at the scribe plus. So that's why. So let's pick up the u, which is the retarded time. Okay. So now if you substitute this in this metric, what you basically get is at the end, if you do the algebra, it's a simple algebra. And then okay. So this is the metric in this. So this is the metric for a unit sphere. Okay. And now what you can do is that you can go to null infinity, go to the future null infinity by taking r to infinity, say at fixed u null infinity at fixed u, theta, and phi. Okay. Now you can now you can look at the induced metric. So as r goes to infinity at fixed u, so you can see that the induced metric. So you have to do a conformal rescaling to get it, but it will look like this. So it's a two-dimensional space. So basically, what it says is that in this u theta phi space, the metric is degenerate because this is a null hypersurface, and this is essentially this metric which you have here. So that is a metric which is induced on a space-like cross section. So basically, you have to rescale this r square because otherwise this will not make sense. But the thing is that so you get a spherical metric of a sphere, and that is essentially, you can think of this as a metric on this S2 which you have, say, in the Scri class. Okay. So these coordinates, so at Scri class, so this is the Penrose diagram, and this is the u coordinate on the Scri class, and the theta phi, so that is the coordinate on this S2. So this is an S2. Okay, and this, of course, this Scri plus, so that's a null hypersurface. Okay, so this is essentially the celestial spheres, and the thing is that why it is an interesting thing, because just from the, if you look at scattering process in Minkowski space-time, okay, so suppose you have some, so here where the scattering takes place, so you have some incoming particles like this, and then you have outgoing particles. Okay, and if you take all of them to be, suppose you take all of them to be massless, then they are the, so asymptotically they are all free, and the thing is that they all hit some point of this sphere, the S2. So now actually we'll make it more rigorous. So that is essentially what we do now. Okay, so we start with the scattering of massless particles. So if there is any question, you should ask me now. Okay, so let's consider momentum P mu, since it's massless, so P mu equal to 0. Okay, and this essentially, if you write it in the Fourier, what you will get is that P1 square plus P2 square is P0 square. Okay, and so you can write it in the, if you scale it by P0, okay, so this is the equation of an S2. You can see with the coordinates, say x, y, z, or say x1, x2, x3. You can think of these as Cartesian coordinates. Okay. And what does this sphere represent? So if you write it in this form, so it is P0, P1, P2, P3. So you can write it as P0, 1, comma, n hat. But this n hat is essentially a unit vector. with components like this. Okay, so this is essentially the direction of motion of the massless particle. So it is important that, well, I should, maybe I can actually do it with some here. So, okay. This is the important thing is that this is the direction of motion. Okay, we are not interested in the, yeah, so this is the direction of motion of the massless particle. Asymptotically, of course. Okay, and now as you vary this n hat, you get a sphere, which is the S2, and that is essentially the, well, I mean, that is if you just draw it from here. So these are various directions of motion, and they generate a sphere. Okay, this S2. Now this sphere, which is essentially the set of directions of motion of a massless particle, that has some interesting thing. So has some interesting properties. For example, so let's use, since it's an S2, we can use the stereographic coordinates. Okay, so Z, it's like x1 plus ix2 by 1 plus x3. Okay, so this is a complex number, and the thing is that the Lorentz group in 4 dimension, actually, well, well, SO3 comma, basically, well, it is not SL2C, which is the actually the double cover of the SO3 comma 1. Acts as the group of global conformal transformations on the sphere. Transformation. So how do you see this thing? So what we do is that, well, so this is essentially a very, well, I mean, this is a standard demonstration. So you start with a null vector P and define a Hermitian matrix, which is like P0 minus P3. Okay, so this is a Hermitian matrix, and the point is that the SL2C acts on P as so it's a 2 by 2 matrix. So SL2C means, I mean, these are ABCDR complex numbers. Just determinant of lambda is 1. So that is this condition. And you can see that the important property here is that the determinant of P is essentially the norm of this 4 vector, which in this case is actually 0. So now with this, you can actually see, for example, from here, since the determinant of lambda is 1, So you can see that the determinant of P prime is equal to determinant of P, or which is the same as that P mu prime. P mu prime is P mu. So this P going to P prime. So this is a Lorentz transformation.
So Shamik, that this is special to 4 dimension.
Yeah, this one is actually special to 4 dimension. You can do this, I think, in 6 dimension also, but there you have to use SL to H. H is actually the quaternions. So that I think one can do. Okay. Basically, the thing is that you just replace this P. Well, I mean, you can have something like P0 minus say P5, and here, well, so I think, well, how do I? Oh, no. Wait. Yeah. So this particular thing, I mean, that you can replace by P1 plus IP2 plus JP3 plus KP4. So that kind of thing you can do. In 6 dimension, I think that you can do. Yeah. I mean that I don't know how useful it is, but the point is that one can do actually. In fact, we have actually done similar thing, but well, I mean it is unpublished. But the thing is that at least in 6 dimension you can do, and perhaps in 8 dimension you can use octon. But well, octonions are more. Yeah, but at least the 6 dimension. So SL to H is the quaternion, so that can be done.
Okay, so basically in 4 dimension, the fact you are using is that a null vector can be written as a bispinner, right?
Yeah, so this essentially, since the determinant of P is actually 0, so I can write this like this P alpha dot as some lambda bar alpha dot. So alpha and alpha dot, so alpha is 1, 2, and alpha dot is also 1 and 2. Okay, so this
but is there any construction where you don't have to rely on this isomorphism? I mean, just the fact that this direction takes value on S2 or in general on some Sn. From that, is there any construction on the action of the Lorentz group?
Lorentz group in 6 dimension, it is there, right? So that's what actually I'm saying. In 6 dimension, I think you can do it.
No, I understand. I'm saying in general, like, can it be democratic in D? That's my question.
Oh, okay. For general D, well, I don't know. For general dimension, yeah, no, I don't know. I'm not. Yeah, I don't know. Yeah, for general dimension, general D dimension. Yeah, I don't know. Yeah, I think, yeah, I mean, we can think about it actually, but the thing is that, so immediately, I don't know how one can do it in general dimension.
Okay, thank you.
Yeah. Okay, so you can see that this P to P prime, so this is a Lorentz transformation, but the fact is that plus minus lambda, they generate the same Lorentz transformation, and that's why SO, you can say that SO3, 1 is the same as SL2C mod Z2. Okay. Well, but that's not the case. So the thing is that, so this is a transformation law. So P goes to P prime where this lambda dagger. And so SL2C actually acts on this P0, P1, P2, and P3. And now, so the question is how it acts on this. So the thing that we have defined as the stereographic coordinate. So let me just, so if you go back to here, so I define this Z as x1 plus ix2 by 1 plus x3, where x1, x2, x3 was this p1 by p0, p2 by p0, and p3 by p0. Okay, so now if you just write everything in terms of p1, p2, p3, and p0, so what you get is this is p0, plus P3, and under Lorentz transformation, this will go to Z prime, which is actually P prime 1 plus I P prime 2, P prime 0 plus I P prime 3, and this you can check that this is given by AZ by B, AZ plus B by CZ plus D. Okay, so this is, so that means the SL2C acts on the space of null directions which is a sphere raised to as the global conformal group. Okay, so this is an important thing, well, so this part is okay. Let me just see what I want to say after this. Yeah. So now there is a way to write this momentum. So now parameterization of momentum, null momentum. Okay, so we can write so Z equals P1 plus IP2, P0 plus P3, and you can solve for this in terms of, so if you solve for this, you can write this P mu as P0 times 1 comma Z plus Z bar by 1 plus Z bar, and this is minus I Z minus Z bar. So I'm just solving for P1, P2, and P3 in terms of Z bar and P0. Okay, and so this is one useful parameterization, but we can actually we'll use one more, which is actually a little more useful. I mean, well, you can do it either way. At Z bar, where omega, I have defined omega as P0 by 1 plus Z bar. Okay, so these by contrast, so you can see that P squared. So this, of course, by construction, if you write your P mu in this particular form, then it is true by construction that P mu equal to 0. Okay, so that means it is null. So now that redundancy is gone, so you don't have P0, P1, P2, P3, but you just have these three independent numbers, which are these omega, Z, and Z bar. Okay, so you can think of this omega as energy up to this factor, this 1 plus Z bar. Okay, now how SL2C acts on this? So under an SL2C transformation, the Z goes to, of course, we have shown this goes to this. It transforms in this way.
In principle, omega can be complex, right? So in that sense,
yeah, actually at the, yeah, so omega actually you can, yeah, so that I will come at when I define the integral basically. So that I think the integral contour you can choose in some way, but to start with it is real actually.
Okay, but at the level of your equation P square, if I choose complex omega, that P square null condition is still satisfied.
It is, yeah, it is still true, and and it is also, I mean that we will actually use is that Z and Z bar they are not necessarily the complex conjugates. So they are just independent complex numbers.
Okay.
So that is the thing. Okay, and how omega transforms? Omega transforms like this. Sorry. Omega into mod of Cz plus d whole square. So this is the transformation law for the omega z and z bar, okay, under an SL2C or a Lorentz transformation. Okay, so now the thing is that, okay, so now how do I do this? So now we have to work with the creation annihilation operator for massless particles.
Hello, Samita.
Yeah.
So initially you introduced this inhilatory variable, lambda and lambda bar.
Yeah.
Is there any connection to Z and Z bar?
Yeah. So this, right. So that's a good question. So let me just mention this thing here. Yeah. So this, I wrote this. So just let me. So this P alpha alpha dot. So that is lambda alpha and lambda bar alpha dot. And this Z that is essentially lambda 1 by lambda 2. Okay. Is it clear? So if so my Z is this P1 plus IP2 by P0 plus P3. Okay. And if I write this P alpha alpha dot as lambda alpha lambda bar alpha dot, then this Z is just lambda 1 by lambda 2. So these are the spinors. So this lambda lambda alpha. So that is the, well, I mean, depending on half zero. These spinors. It will be this here, and then this Z. So it is basically an interesting from the geometric point of view. So this lambda 1, lambda 2, they are basically the homogeneous coordinates of the sphere, the S2. And this Z is the inhomogeneous, or S2 or the CP1, if you think of it in that way.
I see.
Yeah. So that is the relation between these two actually.
So even in general dimensions, this the action of the point action of the Lorentz group on
Right.
SP would basically still be the conformal action.
Yeah, I think so. Yeah. I think yeah. That is still true actually.
Okay.
Yeah, that is still true. Yeah. Yeah. So now let us look at the creation annihilation operator for massless particles. So okay, so we usually write them as say A P sigma, where P squared equal to 0, or A dagger P sigma, where P square equal to 0, and sigma is the helicity of the massless particle. Okay, so now if I use this particular thing, that this P is, if I use this particular parametrization for P, then I can write, of course, I can write them as P omega Z bar sigma, or A dagger omega Z bar sigma. Okay. In fact, you can use like a more convenient notation, which we could call it as A epsilon omega Z bar sigma, where epsilon equals plus minus 1 for annihilation or creation operator. Okay. So basically the annihilation operators are positive energy, like And then negative energy annihilation operators are like creation operators. So that is basically the. Okay, so now given this thing, what we will do is that, so now let me define what is the thing is that this Mellin transformation. So we can define this object phi epsilon h comma h bar z bar. We want to integrate out this omega and define a field which is completely defined on the sphere, the S2. Okay, so it's in this way. So it is d omega. It goes from 0 to infinity, omega to the power delta minus 1, and then I have a epsilon omega z bar sigma. Okay, and this h, we have defined two numbers, h and h bar. They are given by this delta plus sigma by 2, and h bar is delta minus sigma by 2. Okay, so this is the Mellin transformation, and this was introduced in this paper. So now let me give you the reference. So this was introduced in this 2A by Bastersky. So okay, and then Bastersky and Sau actually wrote a very interesting, detailed. Actually, they made all these things much more clearer. Actually, and that was this paper 1705-01-027. Okay. So this is essentially the transformation that we will use. And since now you can see, since the energy is now integrated out, so what you are basically left with is these numbers. So is this numbers h bar. So they are defined as a delta plus sigma by 2, and h bar is delta minus sigma by 2, and z bar that of course remain unchanged. But now the important point is that how does the, so now, so you can see that this object, this phi h bar z bar, so that is an operator defined on the S2, which is the space of null directions. Okay, so now you don't, there is no reference to this extra thing, which is the omega here. So now it is completely localized on the A. So you can think of these objects as if you have some kind of some scattering, massless scattering like this. So you can think of them as operators which are localized here with some numbers like epsilon, h bar, and of course the z bar, which is here. So now, but now the question is that how does so, and we know that this SL2C was acting on this sphere, which is essentially the space of null directions as a global conformal group. So how does it act on this, on the field, which is this phi epsilon h bar z bar? So the SL2C acts on as, so under an SL2C transformation, So this goes to some field phi prime of epsilon h bar, z bar, and this is equal to dw by dz to the power h, dw bar, dz bar to the power h bar, and phi epsilon h bar, w bar, where w is the Lorentz transformation of the point Z, and w bar is essentially the complex conjugate, and h bar we have already defined, right? So they are just given in terms of this delta and sigma in this way. So now from this, if you are well, so I mean we know, I mean if you are familiar with just the action of the global conformal group on primary operators, then you know that this is essentially the transformation law of so this is the transformation law of a primary field in 2D with conformal weights. So in 2D, we have this holomorphic and anti-holomorphic conformal weights, H and H bar, okay? And from here, we know that since it just, so this transformation law, which we have here, okay? So this particular transformation law tells me that the delta, which we have introduced, so which is given by H plus H bar, because you can see that this H was delta plus sigma by 2 and H bar is delta minus sigma by 2. So this delta equal to H plus H bar is essentially the scaling dimension of the field of of phi epsilon and sigma, which is the H minus H bar, which is essentially the helicity. Okay, so let me be more precise here. This is the 4D helicity is the same as the 2D spin of the operator. Okay, so these are the objects which are of interest to us. So these are conformal primaries.
Shamik, is there a restriction on delta for the integral to converge?
Well, the point is that for integral to converge, yes, I mean there are certain restrictions, so I'll come to that. So just let me just finish this thing, then I will come to your question. Okay?
Yeah.
Yeah, just so these are conformal primaries located at different points on the sphere. Now the thing is that if you if I go back to your question, so if you restrict your delta to have this form, say delta equal to 1 plus I lambda, okay, in fact that is, I mean if you base with lambda a real number, okay, so in that case this is actually required for unitary representation. Okay, so delta can have this particular form, and of course your 2 sigma must be z, the integer. So sigma can be integer or a half integer. Okay, so these are essentially what are called the unitary principal series representation of SL2C. Okay. So this is what actually you can do it from group theory, and actually basically I will basically it was done in a paper. So this is 1801-10171. So you can actually like basically the group theory details, some of the group theory details you can find here, and I'll come to more things actually. Okay, so this is basically the story. So now, so if I start with these massless fields, okay, and basically the Fock space creation and annihilation fields, and then from there I can do this integral transformation, and that gives me this conformal primary fields. But the thing is that basically, although this is an useful thing, but it turns out that delta like it is useful to analytically continue in delta. Okay. In fact, that's what we will do. I mean, it is extremely useful. Like we will do in the sense that that is done actually. Okay. So now, why that can be done? So let me now write down what this object. So these are on these AA daggers or this phi epsilon. But now let me define the Mellin transformation of the S matrix element. Okay, so now we know that how the A and A dagger transform. So S matrix, it is essentially you have a bunch of like A, and then you have a bunch of A daggers. So you transform each of them. Okay, and that essentially gives you this correlation function form. So this becomes phi epsilon I, hi bar, zi bar. So this essentially you transform each of them. With a specific delta I which you can choose. And then you have A epsilon I. Oh, sorry, this is not A. Sorry. This is the S matrix. So this is the S. Epsilon I, omega I, zi bar, sigma I. Okay, so this is the S matrix element. Okay, so you have to do this integral transformation on the S matrix element, and then on the left hand side what you get is, you can think of this as correlation function of primaries. Okay,
Samik,
yeah.
Is it necessary to define A dagger and then phi? I mean, I can define S matrix abstractly without defining any like perturbative field theory or something, right? Then can I use say given the S matrix to relate it to the phi as a correlation function?
Yeah, so that can of course be done in the sense that so if you just look at the right hand side of this integral, say of this integral, Then whatever is there actually, so that you can call, say, some m, like m of well, hi bar, zi bar,
Yeah.
each of them, and that will transform just like that. So now I will say that, I mean why it is a. So basically the statement is that the left hand side transforms like correlation function of a conformal field theory. Okay, so that essentially follows from the Lorentz transformation of the S matrix. Okay, and the thing is that even non-perturbatively, you can always define the in state and the out states, right? Like you have the bunch of like A in or A dagger in, and then you have the A out. And I mean, these are basically the free in the outgoing and incoming, and essentially you can consider the vacuum expectation value of these objects. A out, some bunch of A outs, and then okay, and I can define the phi for each of them.
Right.
So that can always be defined, I think. Even non-perturbatively, right?
Yeah. I understand your comment. Just to make sure,
Yeah.
suppose I don't go through this A or A dagger business. Given S matrix, I do a transformation, then still I'll just be able to identify that the left hand side correspond to some primary operator CFT
Yes,
correlation.
right. So how yeah, so I will show actually. So just so I will just immediately show that how this thing will transform. So in fact, so you can just check, for example, the thing which I said here. Okay, so for example, if I look at this transformation law, so let me first prove this transformation law, and then you can prove it in the same way. So let me do it for the scalar case. Okay, so scalar case, which is sigma equal to 0. Okay, so let me just define this in phi epsilon. Yeah.
Okay, sorry.
Yeah.
Since you have drawn the Penrose diagram for the scattering process, so is it must be some kind of a matching condition at C all I 0? Because you are for the scattering to occur, it's like the some certain properties of the field must match at I 0.
Yeah, so that is of course not that way. Yeah, so it is not now actually. So that condition will.
Hello? Hello?
Yeah, so Shamik got disconnected.
Okay.
His microphone got disconnected. So you have to, I think you have to activate your iPad microphone or something. Yeah, maybe internet connection went off.
Hello.
Your iPad probably got stuck. Shamik.
Hello.
Yeah, Shamik, yeah. Your iPad
Hello.
has frozen. Your iPad has frozen.
Hello.
Hello.
There is some. Is there some problem with the internet connection?
Your iPad has frozen.
Yeah,
We can hear you.
Somebody hear me?
Yeah, we
We
can
can
hear you.
Hello.
We can hear you, but we can't see your iPad move. Maybe you can start writing and see whether something is happening.
Hello.
Can you hear us? I think you have to turn up the volume on your laptop.
Hello.
Yeah, can you hear us?
Yeah, now I can. Yeah.
Yeah. So your iPad got frozen. So I think you have to reshare your iPad.
Yeah.
It happens. Yeah, it's happening. I've seen it happening.
Reshare. So I just do share screen, right?
Yeah. Just try him again.
Yeah. Sorry. What is just a minute?
Yep.
Yeah.
Back, I think.
Oh, so is it visible? Okay. Yeah.
Yes.
Okay. So yeah, I think. Okay. So I may take say 3-4 minutes.
Sure. It's fine. Yeah.
Yeah. So I'll just finish this thing for the scalar case actually. So I have defined this operator, and so oh, okay. I mean, if I'm just talking about this case of scalar fields, so I'll just go through this. And then, so now the question is, so now let me define this U lambda, which is a unitary Lorentz transformation. So now I want this to act on this and see how this thing will transform. So here I will basically use the Lorentz transformation property of the creation annihilation operator. So it is a scalar, otherwise you will get some matrices which will multiply this, which depends on some finite dimensional representation of the little group. So this you get epsilon omega, this, and then Az plus B by Cz plus D, and then complex conjugate. So this is how the creation annihilation operator will transform, and this is essentially how the Lorentz transformation or the SL2C acts on this omega z and z bar. So now I have to make a change of a variable. So you can see that this omega time gets multiplied by mod Cz plus d whole square. So this essentially becomes mod Cz plus d to the power 2 delta and 0 to infinity d omega prime to the power delta minus 1 a epsilon omega prime Az plus b by Cz plus d, and then complex conjugate. And this, so this we can see. So this will become phi epsilon h bar Az plus b plus Cz plus d times Cc. So how it transforms? So let me write down the final answer. So for a scalar, it is just easy to check. Now, since for a scalar, h is equal to h bar because the helicity is 0 or the spinless, so it is delta by 2. So you can write this prefactor as 1 over Cz plus d to the power 2h and c bar z bar plus d bar to the power 2h bar, and then phi epsilon h bar. And this is essentially the form which we want, which we wrote down in general. So you can compare this with this form. So once you take W to be Az plus B by Cz plus D, then dW dz in particular, let me write it here. So dW dz is 1 over Cz plus D whole square. Okay, so once you compare this, so this becomes 1 over Cz plus D whole to the power 2h, and this is 2h bar, and then multiplied by this, where W is this. And this is essentially what we have proved for the scalar case. Okay. And now if you use this, you can see that this transformation, this in transformation of the S matrix, which you have on the left hand side. So the way this will transform is essentially is that under an SL2C transformation, since that is a symmetry, so this is equal to, where this W is this. So you can see that this object, which is the correlation function on S2, so it is essentially transforming in exactly the same way as the correlation function of a conformal field theory on the sphere, okay, with the particular h and h bar. Okay, so this is what we essentially want. So this is essentially the beginning of this, but the point is that the next time what we will do is that So this is all about the SL2C, but then next time we will talk about the space-time translation, okay, in this picture. So this will be our next day. But so this is roughly the story, and then we can start from here, and then we'll talk about the word identities, which are essentially the soft theorems, and then we'll see that if we start from there, we can actually compute some four-dimensional scattering and amplitudes in this particular way. So that will, I think, come at the end. But before that, we will also talk about the OP and all these things on the sphere. So this, so some kind of yeah, so it will behave very much like a two-dimensional conformal field theory, but there are lots of extra things also which we will talk about. Okay, so I think, yeah, so for the time, I mean, I'll stop here. So next time I'll talk about the space-time translation. Yeah, so I'll stop here.
Okay, so thanks, Shamik, very much for a very clear lecture. Yes, I can hear some claps as well. Questions? Are there any questions? I think Arindam was asking a question before you got disconnected. So.
Yeah, so the thing is that, so yeah, so he was talking about the matching condition. So that will not explicitly appear in this. And so far what we have done, so that is not required. I mean, it is essentially a transformation. So it is essentially a basis transformation. And I mean, that's how one should basically think about it. Yeah.
And can I ask another question?
Yeah, sure.
Okay, so you started with the, I mean, the motivation for, I mean, studying the flat space holography, right? If I understood it correctly.
Mm-hmm.
Yeah, but apart from that, I mean, is there any observational, I mean, like detectable measures that we can, I mean, interpret from these kind of analysis, like the correlation functions of the H2, like something like gravitational waves, or some, which is motivation for Strominger's review, something like that. I mean, maybe it's kind of stupid question, but I was just wondering.
Thing is that it's not a stupid question. So that's what we want to do at the end. So this is
Okay.
beginning. But the thing is that what I will say that it will not be completely useless, because we have at the end of so at the end, what we will do is that we will compute some scattering and amplitude, some image field scattering amplitude, okay, which are, of course, you can experimentally find them out, I mean, if you want. So it's not completely useless so far, but more practical questions, well, that I think, well, it will take time, and not from this year. So I'll not be talking about the bulk picture in that way. I'll be just talking about, so this talk, so, or this lecture, it is basically about well, you can think of them like, is there a two-dimension, I mean, well, so is there a, well, like, is there a 2D quote unquote field theory which computes scattering amplitudes? Well, I mean, there is a two-dimensional theory which it does, which is the field theory on the string worldsheet. So that computes this thing, but this is not in the same sense. And there may be some way of connecting this to that. But the thing is that which computes 4D scattering amplitudes. So that is essentially the question.
Okay, so you will not be mentioning anything about this memory effect, right?
No, what?
You will not be mentioning anything about
So
this
I'll not,
memory
no, I'll
effect.
not be. So basically, my thing will be essentially bootstrapping a matrices. So
Ah,
like, that is the thing. Like we'll.
okay. Understand. Yeah. Sorry for this.
No, it's fine.
I was not sure
No,
about
no,
what
there is
you
no
meant.
such
Yeah.
thing as a stupid question, please. That is the first rule. You should ask anything.
Go ahead. So ask whatever you want. Actually, yeah.
Yes.
Okay.
So basically, yeah. So I'll be focusing on some kind of bootstrapping of massless tree level scattering amplitude in 4D. So that's type of thing I'll be talking.
Can I ask one question, one very quick question?
Yeah, please go ahead.
So, probably that's what you're talking about. Suppose I have a CFT coordinate, which is a T mu theta theta, theta is a scalar. Then
Right.
I'll have Watt identities, Watt Takhashi identities, basically.
Right.
And, those are semi-local terms, meaning there will be some delta functions. And
Right.
there can be as well very purely a contact term also in CFT. What are interpretation from the scattering amplitude point of view for those? Is there an interpretation?
Well, so the way these word identities will appear, for example, well, I can write them down actually, like so the way we'll actually get them is in like one of the things which we'll get is like something like this. So we are in two dimensions, so you think of this as that, like so this is essentially the leading soft theorem or the super translation word identity. Okay. Or the, okay, I'm just writing this because Sachin is asking this. It will have some form like this. Some say PZ times you have a bunch of operators. Sorry, yeah.
So this is something that you're going to talk about in the next lecture, is that right?
Yeah, but so he asked. He's asked.
You can explain it the next time. So, so you said this will. So just for purely contact term, you said it will be related to the.
What do you say purely contact, like those terms which will, like what kind of terms, like you get the delta functions which essentially come from the like general structure in 4D will be, then you have some bunch of fields.
Right.
Yeah.
So that will give you some over I. Something.
Right.
So these kinds of contact, well, I mean these are the contact terms.
Yeah, you said this will be related to the say soft theorem or subleading soft theorem. I was asking more pure contact term, which is a bunch of just delta function, nothing else, just a bunch of delta functions.
So for example,
say example, say 555 is delta x1 minus x2, delta x1 minus x3, that kind of thing.
555.
Yeah, I was just giving you an example. Let's say J55 would be say some derivatives acting on delta x minus x1, delta x1 minus x2, x1 minus x3, that kind of thing.
Just J55.
Yeah, say J or stress tensor 55. You can have purely contact term, which are two derivatives, which will be just defined at a point. Right? Is there an interpretation of those as well?
Well, so those types of word identities, at least to my knowledge, I mean, those do not appear in this case, at least. Like the things that I will be, because the word identities that you get, the word identities and soft theorems, so they are basically the same thing. So there, of course, you don't get things like that. I mean, you get standard looking things, like well, standard.
Yeah, maybe you can again ask the question next lecture.
Do you know of an example where this could appear in?
Maybe Sumik, I'll send you a separately. I'll talk to you separately, maybe. Since, or maybe not.
That this super translation, super rotation, or the SL2C of algebras that we will have. So those will have very standard forms actually. So those will not be.
Yeah.
Yeah.
Okay.
So not encounter things like that.
Yeah, I can ask you a question, Shamik. So the way that you described the setting up when you describing Mellin transform, and then also you're describing the Mellin transform as a scattering amplitude, it did not seem essential, at least to me, that you require to consider only massless exchanges. Is that what you're going to do? That even the exchanges will be massless?
Yeah. So I did not talk about the massive case. In this case, of course, the massless exchange is at least in this case. Well, you can do this thing purely from the group theory point of view, and there the massless thing is extremely clear. That I mean, where the like what is the essential difference between the massless and the massive, and that is essentially discussed in what I have done. I mean, in this reference, but from a more algebraic point of view, I think. Well, the way you write the p mu, that essentially depends on you.
So that's the
And
external particles. I'm just wondering, why shouldn't the blob, I mean, the picture that you're drawing, why can't exchanges be masked?
the exchange, the massive.
Yeah.
So the massive exchange can definitely be part of this actually, because these are only external things.
Right. That's what I thought. Yeah.
Right.
I mean, the only place where actually the masslessness or whatever comes in is when you're doing it in a perturbative sense, where you're sort of expanding the interaction term also in terms of creation annihilation operators. So if you want to do that in a perturbative sense, then I guess you require masslessness.
Yeah, but in this case, we don't have any perturbation theory as such.
Right.
Because these are only the asymptotic states actually, which we have like also in some non-perturbative sense actually. Now the exchanges, so those are the Feynman diagram or the perturbative way of looking at this. But if I just look at the S matrix, then of course those will not. Those will not appear at least at this stage. Yeah, for external massless things, yeah, you can have massive exchanges, but as long as the external particles are all massless, this thing will go through, and it will transform in the same way, and it will just be
right. Okay. Any other questions? Maybe I can stop recording and you can continue if anybody else wants to ask any further questions.